So let's go statistics of the extreme, statistics of extreme events. So we are interested, and I'll do some calculation in dimension 1, but it's not going to be that different. So you start with a point x, and you generate your trajectories, and you have n of them. So you have x1, xn, let's say n Brownian motion, n particles moving by Brownian motion. And you're interested, let's call it Ti, or tau, yeah, let's call it tau I is the first time that your particle xi will reach the boundary of the absorbing boundary, which is here the omega A. And this is reflecting everywhere, and this is the domain omega, right? So you're interested in the time tau, which is the infimum, let's call it tau n, the first time for the fastest, that is I have tau 1, tau n. I'm interested in the statistics of this, and more specifically, this is a random variable, right? So this is a random variable, and so you're interested in the expectation. What is the average? If you average of a realization, you're interested in what is the time for the first one to arrive, which is the mean time of the fastest. Okay, so let's go now into, so you're interested in this. This is the first thing you're interested in. The second thing would be the distribution. So the probability of tau n less than t is a cumulative distribution. Cumulative distribution. You can also be interested in when this is equal to t. You know, this is also of interest. This is just the derivative. And in particular, how this so you want to calculate this with respect. So you want to do some computation. So we will be able to do computations only when n is large. So what is called asymptotic calculation, a computation for n large, when the number of particles is large, for n large. And you are interested in how this time will depend on n, on the geometry, that is the fact that there is certain geometry, and on the dynamics, the fact that it is a Brownian motion. And the fact here is we have a Brownian motion. So if you change Brownian motion, if one of these is changed, the geometry, the n, you might think that this will affect your time. So that's the goal, is to calculate this. Okay, so that's the goal. So let's start. So we're interested in doing this calculation for n large, which means the formula will only be true for n large, not for n small. Okay, so now let's start the calculation. I'll show the calculation in dimension 1 and explain what we did it in high dimension. So let's start with computation in dimension 1. So for this, because the particles are all independent, so this is what is called IID, independent identically distributed particle. So the probability that the time tau 1, I mean the tau n, is less than t, you agree this probability that it's 1 minus the probability that tau n is bigger than t. There's no very sophisticated now. But the probability if tau n is larger than t, it means that the particle has not escaped. The first one has not escaped, which means all of them are still inside. The fastest one is still inside. So this is 1 minus the probability that they are all inside. Probability that they are all inside. And if they are all inside, it means that this is the probability. What can I say about tau I? That tau I is, tau 1 is still inside, tau 2 is still inside, and so on. Tn is still inside. So the probability of this being inside, and this being inside, and this being inside by the law of probability, because they are independent, this is just the product. So this is 1 minus the probability. So if it is the product and they're all independent, I can take one of them. This is the first one. So 1 bigger than t to power n. Right? So this is 1 minus the probability, or 1 minus the probability that tau 1 is less than t to power n. This is just some little calculation. So, which means that if you are interested, for example, if I take the derivative of this quantity, probability that tau n is less than t, this is, so constant is a constant, 1 minus this is 1 minus this probability, tau 1 less than t power n minus 1 with a minus, and then I have to use the derivative of this, which is the derivative, which is the probability that tau 1 equals t. Right? Yeah, sorry. There's a minus here, it cancels, so there's a plus. Okay, and this is n, I forgot the n. It's n times this. So this is n times probability that tau 1 is larger than t to power n minus 1, probability that tau 1 equals t. This, if you remember the class of last time, this is called the survival probability. So this is n times s of t to power n minus 1, probability of tau 1 equals t, where s is called the survival probability. Right? This is a survival probability. So you remember the survival probability. If you have, so now we should go back to the calculations in terms of. So yeah, it's important that you follow the class specifically and learn the class. So if you have a Brownian particle, what is the description of the Brownian particle? You remember, we can use the Fokker-Planck equation. This is what we did last week. So the description of the transition probability function, P of t, so the probability density function, which tells you where is the particle when it started at position x, it makes a transition at position y in time, at position y at time t. This is solution of dp dt equals, so suppose I start at y, sorry, and I go transition to x. So this is solution of d Laplacian p for any point x inside the domain. It satisfies dpdn equals 0 on the reflecting part, and p equals 0 on the absorbing boundary, d omega a. Right? This is exactly P's solution of this equation. So the probability that the particle is still inside is what? S of t. It means that from x to y, you made any transition to any point inside the domain. You started here, you could make any transition at any point. So if you want to summarize this is obtained by the integral over all points in the domain. You started at position y and you make a transition to x and you integrate over your volume. This is the survival probability. Which means that if I want to calculate this, I have to calculate this quantity. And if you start at position y, I forgot here to write that this requires that p t for t goes to 0 converge to the delta Dirac at x. That is, I'm sorry, at y. It has to be, you know, everything is located at this point. Okay, so now how you calculate this quantity this time? So the expectation of tau n, you remember, this is, if I know how to calculate this probability, this is the integration from 0 to infinity of t d dt of the probability that tau n is less than t by definition. dt. That's, you have your probability density function multiplied by t. It's the first moment. The first moment, you know, you remember, right? You have a variable x, expectation of x is x p of x dx. That's all right. So this is exactly what we just calculated. This is what we want to calculate. It's here. So this is we can do integration by parts. If you integrate by parts, you integrate this and you differentiate t. So if it's t, so I integrate this by writing probability of tau n less than t minus 1 the constant from 0 to infinity minus integration from 0 to infinity. If I differentiate t is 1, and if I integrate this plus here it's 1 minus the probability that tau n is less than t dt. At 0, this is probability that at infinity, probability that tau n is less than infinity is 1. So 1 minus 1 is 0. And at 0, because I have a t here, this is 0. So I'm left with integration from 0 to infinity. 1 minus this is just the probability that this is larger than this. Tau n is larger than t dt. Okay, and all right, and now what is this quantity? This quantity, I can calculate it from here. I can use this formula here. So the probability, 1 minus this probability is probability of tau n. I just put this into this part and this into that part. So 1 minus this, it's exactly this one. So this probability larger than t, which is 1 minus this, equals 1 minus this, and 1 minus this is this. So this is a probability that tau 1 is larger than t to power n. So this is integration from 0 to infinity of probability of tau 1, the first one of the particle, larger than t to power n dt. That's beautiful, because we say that we have n particles. I'm interested in the time, and finally what I have to calculate is the integration from 0 to infinity of the probability that the first one particle is still inside at time t to power n, and then I will have to just go to the limit n large. So this is, now I have shrinked the question to do this calculation. If I know how to do this calculation, I'm in business. Remember, suppose you have to do the simulation. Suppose you have to do the simulation. Well, if you have n large, for example, you start with n equals 10 to the power 3, 10 to the power 8, whatever, n large. So you have to simulate. It costs time. It costs simulation time and then in the end you can calculate the time, but this will not tell you, oh, this depends on the parameter. Then you have to vary parameters if you want to understand this. That's why an asymptotic calculation is important. That's why people have developed calculation of this type. Okay, so now let's do the calculation in dimension 1. So you see how it works. Okay, so I'm going to dimension 1, calculation. So let's formulate the problem in dimension 1. You start, let's say, at a position y, and suppose you are going to be absorbed at 0. And at 0, everything stops. And so you have a Brownian motion. You know, a particle goes like this, and eventually gets in here. You know what happens if you do this mean for one particle only? Because you can make here long excursion and very long excursion, and you can go outside the board. So if you average over all of this, what is the time for the first one to escape? What do you think? If you average over all these possibilities. The time here, because it can go very far away and come back, so you have more and more time. So if you average over all realization, the time to go from here to here will be infinite. Because it's infinite in that direction. But if you look at the time for the fastest, if you have at least 2 or 3, you can show that it is finite. Because the fastest will escape. And now let's do it for n large. If you do n large, the fastest, because the fastest means you have to take the minimum, basically the motion. If you have n of them, you look at the one that has the minimum position, and the one that has the minimum position will actually drift to 0. So how do you show this? All right, so let's go slowly. How do you study the position of the particle? You solve dp dt equals d ddp dx squared. This is a diffusion equation. That's what I wrote here in dimension 1. The particle is absorbed here. Absorption, what you remember what it means? Absorption. The absorption is on 0, which means P0 at any point, at any moment of time t equals 0. Okay, so how do you solve this equation? And at time 0, you have a delta Dirac at position y. So in general, suppose you have the general problem of solving this equation. Suppose you are in infinite line, you don't have absorbing, and you have a delta Dirac. You know what is the solution of the diffusion equation? It is called the this is the most well-known function in mathematics after polynomials. That's the Gaussian. So in general, the solution, you start at position y and you make a jump to x in dimension 2. In dimension 1 is x minus y squared divided by 4 dt, 1 divided by 4 pi dt. When t goes to 0, you have, you know, the classical shape of the curve. You are at position y, and at time 0 you have your delta Dirac, and then as time goes on, you have, you know, your distribution that becomes wider and wider, and then until it collapses to 0. That's the classical solution of diffusion that you should have learned in the first year of university. How do you modify this to satisfy this equal 0 at position 0? It's not, because when x equals 0, it's not 0. It's this. When I plug 0 in here, I have to remove something to make it equal to 0. Is that clear? So it's not a solution for this problem, it's a solution for the entire problem. So I need to modify this. So the way I modify it is I'm going to do what is called, in mathematics, the reflection principle, which means you take pt of x and y and you reflect it. So you change x in minus x. So you have exponential minus x minus y squared 4 dt divided by 4 pi dt minus exponential x plus y squared divided by 4 dt divided by the same thing, 4 pi dt. This is solution of this equation in the positive space. is for x positive. This will give you the delta Dirac when t goes to 0, and this will give you nothing because it peaks when this is 0, but this will never be 0 because x is negative, so this will collapse to 0. For x equals 0, what do you see? For x equals 0, this is equal to minus y squared, and for x equal to 0, this is also minus y squared. So this minus this is the same, so this is 0 at x equals 0. So this is the solution of this equation. So that's the solution that is telling us what is the probability to find the particle given that it was positioned at y, it moved to x at time t. So that's exactly what it is. All right? And so now what we need to calculate is this probability tau 1 to larger than t to power n. But then I showed to you that this probability of tau 1 bigger than t, this is the survival probability. That's why we've written it as t to the power n minus 1. So I need to calculate s of t, which is a survival probability. So this is a survival to power n. That's what I need to calculate. So let's start with s of t. S of t equals to what? The integration from 0 to infinity. I have to integrate over the entire domain of p, t, y is where you start, x, dx. All right, I need to calculate this. So how do you calculate? So let's replace everything. So this is integration from 0 to infinity of the first term, exponential x minus y squared divided by 4 dt, 1 divided by 4 pi dt, square root. This minus the integration from 0 to infinity of exponential x plus y squared divided by 4 dt, dx, dx. So here I'm going to change variable. I'm going to look at variable w equals x minus y divided by 4 dt. So this is equals to what? This is exponential minus u squared du, dx, du is dx divided by 4d, which is this here. So if I replace dx by du, it's du, okay, that's right, du 4dt divided by 4dt pi square root. And then I'm integrating here when x equals 0, u equals minus y divided by 4d delta t. And I do the same here. I have to I take u or v, whatever, v equals x plus y divided by 4 dt. So it's more or less the same, except that instead of minus here, I will get, when x equals 0, I get plus y. So this is y, 4 dt, and I forgot the square root, exponential minus v, which I call it u again, u squared du. Alright, so this I'm left is 1 over square root of pi, because everything cancels except one term. And here you see this is the integral. If you're on the line, here you have to integrate from y to infinity. Here you have to integrate from minus infinity to minus y divided by something. So if I integrate from minus infinity to plus infinity, this I need to I want to complete this from minus infinity to this term. So I got, I can always write it. It's integration from minus infinity to plus infinity. And if I do this, I need to subtract the integration from minus infinity to minus y divided by 4 d delta t minus this. You agree? I write this quantity from minus infinity to plus infinity. So if I do this, I have to subtract what I've added from minus infinity to minus y. So the integral of this u squared u is exactly square root of pi. This I'm telling you. So this is something like 1. And integration from minus infinity to minus y and infinity to infinity.
2 times.
That's right. This is exactly twice. So this is minus twice square root of pi. Integration from y divided by 4 dt square root plus exponential minus u squared d. Okay, so let's continue with the calculation. So this is s of t, and I'm interested in s of t to power n. So I need to calculate this to power n. Okay, let's write it this way. Maybe before this, I want to okay. Okay, let's do it. S of t to power n. It's exponential n log of s of t. You agree? That's elementary calculation. So what is log of 1 minus x when x is small? This is x. No, it's minus x. That's right. And x here is what? Is 2 square root of pi integration from y to 4d delta t plus infinity exponential use du. Because when t is so we will see that what is important in here, we'll do this calculation, it turned out to be equivalent. T small means what? If y is positive, because y is there, so y divided by something which is small is something large. Something large, you integrate something large to infinity, this is something small. So what you need here, and I show you the calculation, we can show that you can do integration by parts. This is 2 pi, and this is equivalent to exponential minus y squared divided by 4 dt, and I have to divide by there's a 2 so 2y divided by 4 dt, and it's 1 minus something. It's 1 minus 1 divided by 2u squared, which is y divided by 4 dt squared. This is called an asymptotic expansion plus. Right, okay, you understand what I'm doing? If you integrate exponential minus u du from x to infinity, it's like you can say that this is 2u divided by 2u, right? I didn't do anything. 2u. So this is, you can integrate by parts. It's exponential minus u squared. This is this function that is I integrate, divided by 2u, and there's a minus from plus infinity to x. So minus the integrand parts. So at infinity this is 0, and we are left with exponential minus x squared 2x. That's what I wrote here. And then I replace x by this. So x squared is y squared divided by 4dt, which is here. 2 is the 2 coming from here, and x is this. And then you can continue the expansion. Okay, so we just need here the first term. Right, this is analysis. All right, so once we have this, we've seen that this is minus x. So this is exponential of n. Log of s, this is minus x. And x is this, which is this. So x is 2 pi exponential of minus y squared divided by 4 dt divided by 2y. And then there is a square root here that is missing, multiplied by 4 dt square root. Yes. Okay. So what I need to calculate, it's st. This is what I calculated here is s. Sorry, let me start again. I wanted to calculate integration from 0 to infinity of the probability, yeah, okay, that's correct, of tau 1 bigger than t to power n dt, which was integration from 0 to t of s of t to power n, which is integration from 0 to infinity of exponential n, the log of s. All right, okay, dt. So, yeah, okay, what I wrote was correct, and I have to integrate this from 0 to infinity dt. All right? So I'm left with this integral. If I know how to calculate this integral, I will find what I need. So at this point, I will let you do the calculation. I will guide you for this. You have to change variable in this integral and choose u equals y squared divided by 4 dt. That's the new variable that you are going to select. And for this, what you need is to, so if you calculate yeah, if you do this, all right, let's see what we get. So you get integration from 0 to infinity of exponential minus n 2 divided by square root of pi. Okay, there's a square root of 4d, and then you need to change t here. It will be changed. So we have a square root of t. So what is square root of t? Is y divided by 4d u square root. So this is y divided by 4d 1/2 u 1/2 exponential minus u divided by 2y, and then we have to say what is dt, right? So dt is simply y squared divided by 4d u squared du. So this is du divided by, with a minus, 4d u squared. Okay, so y and y goes away. So we have exponential here of all of this. Okay, and now there is a new variable which I'm not going to. No, I'm not going to do the calculation. You are going to take w equals exponential. No, sorry. So I think I made a mistake. It's 1 over u. 1 over u equals this. Okay, let's do it again. I start from scratch. 1 over u equals this. So let's see how it becomes. You integrate from 0 to infinity, exponential minus n. 2, okay, the 2 and 2 goes away. So it's 4d square root of pi, square root of this. And then I have square root of t. So t is what? Is equal to y squared divided by 4dt, 4du. So square root of t is y divided by 4, and then I have the square root of u. Then I have exponential minus 1 over u. Great. And dt is simply equals to y squared divided by 4d du. Alright? So 4d and 4d goes away. You agree? Check that I'm not doing any mistakes. Yes, that's correct. And now there's another change of variable, which is w equals square root of u exponential minus 1 over u. So this is an exercise, and you can find the rest of the calculation in the paper with Kanishka, in Basnayake, and myself, Schuss. This is in 2018 in Journal of Nonlinear Science. But you can do it as an exercise. Now you just change the variables. You have to integrate by parts. So this y squared divided by 4d is there. It will not change. And what you find when you do this calculation is 1 over log of n divided by square root of pi. And I think there's a mistake somewhere. Why I'm left? I think the y disappeared. That's right. The y goes away. So there is a little calculation here. I leave it as an exercise. Again, as I did, you have to integrate by parts. That's the fundamental result of tonight. This is fundamental. So what are we understanding? What are we understanding from this result here that you are seeing here? What do you think? Now it's time to understand what the formula means. Y squared divided by 4d log of n. What have we learned? We learned that the time to escape here is the distance squared. If you remember Brownian motion, if you want to escape, if you have a disk, if you are at the center of the disk, you want to be absorbed, the time to escape is r squared divided by d, or 4d. So you have this notion of distance squared, the diffusion you have. But what is interesting, it's log of n. Log of n, which means what?
Because it's 1 over log of n.
Yeah, so you reduce the time.
The bigger the n, it tends to be 0. So
yes, but what are you noticing? What is interesting in log is that if you take 1 million particle, are you going to decrease the time by 1 million?
no.
That's right, because log, what is log of 1 million? Log of 10 of 1 million is 10 to the 6, so this is 6 log of 10. 6 log of 10 is what? Log of 10 is what? 10 is like 3, it's like 9. 9 is 3 by 3. 3 by 3 is log of 3 multiplied by 3. So this is 18 multiplied. What is log of 3? About 1. Let's say. So this is no more than 18, 20. So you divide by 20 by multiply by when you have 1 million, which means that the time of the extreme is not that reduced if you increase the number of particles. And that suggests that if you think about the spermatozoa problem, the fertility problem, that's why you have such amount of quantities. If you want to go somewhere, where a place where you don't know it very fast, because it's not going to decrease that fast. If you increase n, or you have to increase n. If you increase n exponentially, still you can go with 1 over n. Right? So that's important. And we've learned that in that case, the geometry has nothing to do with only the distance is important. There's nothing else, the distance squared. Okay, so I want to say 2 more things and then we'll make a break and then we'll move on to the second aspect of the class. So about the second aspect of the class, which is the navigation. All right, how does this change in dimension 2 or 3? So I'll show you in a second. I'll project back because I will not do the calculation, but I just want to write a little bit what it is. What do you think about the generalization of this in higher dimension?
I mean, if y squared is your distance, then it's just a distance in higher dimensional space.
That's right. That's very good. That's very good. That's why if you have a complex geometry, what really matters is called the geodesic, the shortest distance. And that's very interesting because in a very high dimension, suppose you're interested in finding something in the web, in where you have a high dimensional network. You need to find a piece of information and you want to send many requests. So the time for the first one to get the request will basically use some kind of shortest path in your graph. And it comes from here. So these are our remarks. So the remarks are as follows. In dimension n larger than 2, if you have, for example, a domain, you're interested in how long it takes to escape from that domain. So it turned out that, so I'll give you the result. I'm not going to do the calculation. The calculation are more involved. But dimension 1 is enough to grasp the idea. So in dimension 2, if you're in dimension 2, for the first one to escape among n, you have the distance squared. So this is the distance from y to the boundary squared divided by 4d log. And in dimension 2, it's again, you have log of n, but what is in the boundary, what is seen here is log of 1 over epsilon, where epsilon is the ratio of absorbing to the total boundary. Right? This is the ratio of this divided by everything. Again, this is an asymptotic when n is large. It's not true if n is not that large. So as Jim said, it has to deal with the distance square. This is true in dimension. So in dimension 3, you have the same except of log of n. You see a bit of the boundary. You see the shape of the boundary, and that's it. So this is one thing that is happening in dimension 2. There is another thing that it's important to note. This is the second point of these remarks. Is suppose now you have some distribution in the initial position. So suppose we have an initial distribution with a so suppose the initial distribution is not a Dirac. Initial distribution, what is the role of the initial distribution? Suppose you start at position Y, you escape at 0. But suppose now, for some reason, you have a shape. You have a shape. That is, the probability to find the particle here is not 0. It's little, but not 0. Or you can go even to the case where suppose it's uniformly distributed. That is, you have a certain probability to start a particle very close to 0. How would that affect the time? Because if there is a probability to find your particle, to have a particle at time 0 here, then the time has to do with the distance that we just mentioned, which the distance squared to find the particle, but the probability might be small. So you have to integrate all of this. So there is here a change. It's not anymore log of n for some distribution. And I'm not going to show that to you just as a result. So the time to escape for, if you're even in dimension 1, but you have n particles in dimension 1, but you have a distribution, for example, the distribution is uniform, right? Suppose it is uniform in this domain, then it's a constant divided by n squared. Suddenly it's much more drastic because you can find particles. Why n squared? It's the result of the calculation. So again, this is recent calculation we've done in the lab, but to show that the position is important, the distribution is important. Okay, and the final remark, number 3, and then we'll make a break, is suppose you have a Poisson process. What do you think? So Poisson process means exponentially distributed. So the probability that tau is less than t, larger than t, is exponentially small, exponential lambda t. So suppose I have a process like this. Poisson process is very classical. So if you redo all the calculation, what do you get? Well, you remember it's probability to the power n. What we calculated is probability tau bigger than t for n particle. If it's an exponential, it's easy.
1 over n?
Yeah, it's exponential lambda n t. You have to integrate this from 0 to infinity. You have to integrate this. And what is this?
1 over n.
It's 1 over lambda n. So for a Poisson process, yes, you have a Poisson process, which means it's usually independent of the geometry. And then, yes, if you look at the first one, or the fastest one for an ensemble of Poisson process, because there is no geometry, it's 1 over n. It's not anymore the log. Okay? All right. Let's stop here. Let's make a 2 minutes break. And then we'll do 20 minutes. I think I will not have much time, but I think it's important we start today about navigation in the brain.